The other type of problem from 1.7, in addition to mixture problems and distance uniform motion problems, the last type is uh, job problems. And so maybe the easiest way to think about it is rate times time equals one job. So for example, it takes half an hour to wash a car. Your rate is 1 over 30, so you complete 1/30th of the job every minute. So it takes you 30 minutes, so your rate of 1/30 times the time of 30 multiplies together to give you a one job. So let's speed that up to get the story up, and then we'll start talking about how to solve this. So it takes Estefania 6 hours to paint a house. It takes Larry 8 hours to paint that same house. How long would it take for them to paint that same house together, assuming that they're not going to fight or slow each other down or anything like that? So they're just working together at their rates. So what we'll do is we'll set up a little chart to kind of organize our thoughts. So we're going to do Estefania, Larry, and together, and we'll have rate, time, and one job. Okay. And we're going to go ahead and put in the time. So it takes Estefania 6 hours. So her rate would be 1/6, and 1/6 times 6 hours is one job. Larry's time is 8 hours, and his rate is 1 over 8. And 1 over 8 times 8 is one job. Working together, we don't know how much the time is. We're just going to call it T. It might be 2 hours. We don't know. The rate would be 1 over T. Just like the rate for Estefania, 6 hours takes her to do a job. The rate is 1/6 an hour. We get 1 over T, and it's equals to 1. So what we got to be careful about here is what is equal. If I say Estefania plus Larry is equal to time, that's not really true. That would be that Estefania and Larry take 14 hours to paint a house. Well, that's more time than it takes either one of them to do separately. So what's really equal here is the rates. So Estefania's rate and Larry's rate, add those together, that's going to give them their together rate. So it's going to be a little bit different. So we're going to say the rates are equal. So Estefania plus Larry is equal to their working rate together. So 1/6 plus 1/8 is 1 over T. So we're going to have to do fraction busting. We're going to have to multiply by the LCM. The LCM here is 24T. We'll multiply everybody by 24T over 1 because they're all fractions. And we'll go ahead and do a little bit of canceling. Combine our like terms and divide by 7. Okay. So after all that work, it takes them about 3 3/7 hours, so that's roughly 3.5 hours. Does that seem fairly reasonable? I would say that's a fairly reasonable answer. We didn't get something like 10 hours. So if they got 10 hours, then they weren't working the whole time. Maybe they got distracted or took a long lunch. Who knows what. Okay. So let's do another example. And I think this one will take 2 slides just because the math gets a little bit long. So let me fast forward through all the exciting word stuff. And so we have 2 tanks of different sizes are used to empty. 2 pumps of different sizes are used to empty a tank in 5 hours. The larger pump can empty the tank in 4 hours less than the smaller one. If the larger pump is out of order, how long will it take the smaller pump to empty the tank? So we'll go ahead and set up big, small, and together. So instead of Estefania, Larry, and together, we have big pump, small pump, and together. We'll have the same setup, rate, time, and a one job. So what I'm going to fill in first is the together rate. Because I know it takes them 5 hours together, their rate is 1/5 of the tank is emptied per hour. And then where it gets a little bit more tricky is with big here. So I'm going to go ahead and fill that in. So what we'll go ahead and do is we'll call the rate for the smaller tank. So if it takes 4 hours less, that's the rate of the small minus 4. That's going to be the big tank's rate. Or I'm sorry, the big tank's time. The rate is going to be the reciprocal, 1 over r minus 4. So r minus 4 might be a nice number like, I don't know, 8. Then the reciprocal will be 1 over 8. We just don't know what it is, so we just call it r minus 4. The small tank is just going to be, has a time of r, and its rate is 1 over r. And it's just like the last one. The rates are going to be equal. Okay, so we have 1 over r minus 4 plus 1 over r is equal to 1/5. And we're going to have to fraction bust this one. So the LCM here is 5r, r minus 4. So that's what's going on right here, is we're just multiplying everybody by the least common multiple. And then cross-canceling a bunch of stuff. So if you need to, you can always pause and slow this down if anything is, if it's going a bit too fast for you. But, you know, the math stuff that we've already done a bunch. So just fraction busting, canceling out like factors. So I got 5r, and then I'm going to go ahead and distribute here and here. And then I end up kind of running out a little bit of room here on this slide. So what we're going to do is we're going to go ahead and continue this right here. We're going to bring it on the next slide and finish this problem up. Okay. So just rewriting, and this is a quadratic. I'm going to combine like terms, and we solve quadratics by setting one side equal to 0. I'm going to find my ABCs, and we're going to plug it into the quadratic formula. So go ahead and do all that fun stuff. Of course, you can use your calculator for this, just don't punch too hard on those keys. So working this all out, I'm going to end up getting two answers. One of them will be good, and one of them maybe may not make too much sense here. So I've already crossed one out, and I've told you what the answer is, so let me kind of go through why we threw out the other one. So we either get 12.4 roughly or 1.6. In the last example, I threw out the negative answer, and that often happens because, you know, maybe we're solving for time. Negative time doesn't make a lot of sense. Negative distance doesn't make a lot of sense. Negative speed doesn't make a lot of sense either. But here, both our times are positive. But if we think about it, the two pumps working together took 5 hours. And this is solving for just the small pump's time to pump out the tank. So if the small pump only took 1.6 hours, then with the larger pump, then it should take even shorter than that, which is already shorter than 5 hours. So 1.6 is not a reasonable answer. It makes more sense for it to be 12.4 hours. The smaller pump is going to take, at minimum, more than 5 hours. So that would be what we would want for an acceptable answer. And just like all these other problems, there's some variations, but they all boil down into using the, you know, these are job problems, or the distance equals rate times time, or the mixture problems. They're very similar. The more problems you do, the easier they get.